Hi, I'm Dr. J, and this is a video about probability. Now, I have a number of videos about probability. This is the first in a series of videos about probability for a particular class at Iowa State University, Stat 587. But feel free, if you've gotten here from some other means, I hope you enjoy the video. This video is meant to be an introduction to probability, but it's really a very quick introduction, despite the length of this video. Probability is the mathematics behind calculating things like, what's the probability of flipping a heads when you're flipping a quarter? What's the probability of rolling a 1 on a 6-sided die? What's the probability of getting an ace of spades out of a well-shuffled deck of cards? But probability is much more than that. Probability leads into the concept of random variables, and then it leads even further into the foundation for the field of statistics. And that's really where we're headed in this long series of videos. The series has 3 parts. There's a probability part, a statistical inference part, and a multiple regression part. The probability portions are 5 videos long, I believe, and this is the very first of those videos. Now, in order to talk about probability, we need to talk about the mathematical foundation for probability, and that is set theory. So we're going to talk a bit about sets and their operations, but very quickly we're going to get into the definition for probability and the uses of probability after that. The next videos in the series talk about random variables and their distributions and that kind of content. So before we jump into that mathematical definition of probability, we're going to first talk about interpretation. And this is something that I think everybody should keep in mind while they're learning about the mathematical foundations of probability. Always think about how can we then apply this to the real world for real data. And so when I ask the question, what do people mean when they say probability or its synonyms, things like chance or likelihood, or even odds, which isn't quite a synonym, but it's related. When they say, what is the probability of something happening, what do they mean? What is it that they really mean in a technical sense? What are they talking about? So right now you should perhaps pause the video and think to yourself, when's the last time I heard somebody say the word probability in the context of a real world event? And think about what is it that they really meant by that. I'm going to give you a couple examples here. So one example, this is being recorded in the summer of 2020, and therefore COVID-19 outbreak is hot and heavy. And so we might say something like, by the way, I have no idea if this is true, but what's the probability that the COVID-19 outbreak is done, in some sense, by 2021? Let's say that's 4%. If I were to say that, what is it that I mean by that statement? Here's another example. We are in the middle of a political election. So what if somebody said the probability that Joe Biden will win the presidency is 53%? What does that mean? Finally, here I'm going to use a synonym. Suppose I say the chance I win a particular game of solitaire, pick your favorite, is 20%. What do I mean by that? And so there's 2 general ways that people have interpreted or applied probability to the real world in these contexts. And they are relative frequency and personal belief. So here's the relative frequency version. So relative frequency says it's the proportion of times an event occurred over the total number of times that you attempted for that event to occur as the number of those attempts goes to infinity. And so this really makes sense in the context of the third example that I have. What's the chance that I win a particular game of solitaire, right? I can imagine myself going and replaying that game of solitaire over and over and over and over and over again. And perhaps on average, I win it 20% of the time. And so that's a relative frequency interpretation. But it's a little bit harder to imagine how to interpret the other 2 questions that I asked in terms of relative frequency. What's the probability that Joe Biden wins this election? Well, there's only one election. We can't really repeat that election over and over, right? Because number one, presidents in the U.S. only have a limit of 2 terms. And so at most we could ever do it twice. So this relative frequency notion kind of falls apart. The first example that I gave, right? We're in the middle of COVID-19. 19, because it occurred or started in 2019, and therefore we can't really have a COVID-19 again. So there's, again, no real relative frequency interpretation that I can see for COVID-19. So the other interpretation that people have is an interpretation based on personal belief. So I might say something like the probability that Joe Biden wins this election is 53%. And what I say about that is a degree of belief that I have about that event occurring. And that's his personal belief perspective. The nice thing about this personal belief perspective is that you can apply it to every event that's out there, right? So you can say, I have my personal belief of COVID-19 ending by 2021. I have my personal belief about Joe Biden winning the election this year. I have my personal belief about this next game of solitaire I'm going to win, and about the game of solitaire after that. And so it can apply to every situation. So that's appealing. What's not so appealing is that you can have your personal belief, and then I have my personal belief, and there's no reason that those two need to be the same. And I'm okay with that because I think that we all have different experiences, and then therefore our personal belief should be different. Okay, so that's all I'm going to say on this topic, at least for now. We're going to move and shift into the mathematical foundation for probability, but I want you to keep this idea of interpretation, in particular these two, relative frequency and personal belief, in your mind as we go through that mathematical formulation, and in particular as we try to apply that formulation, that foundation, into real problems. All right, so I mentioned before that probability is based on set theory because it's really a function of sets, and so we're going to have to talk about sets a little bit first. I guess before I get there, I'm going to talk about a simple example of when we might use the word probability. So let's say that I'm sitting at home and I'm trying to connect to the internet with my laptop. And so I'm going to call that event, that successful connection to the internet, an event C. And I know, based on my personal history with my personal Wi-Fi and with my ISP, that let's say it's not very good, and I have a 90% chance of connecting. And so what I want to write is something like this. Well, the probability of this event C is equal to 90%. Or written out like that, we say probability of C is 0.9. Now, but to go much further than this, in order to calculate these kind of probabilities in more complex scenarios, we're going to need a mathematical foundation in which to calculate those probabilities. And so that's where we're headed. Okay, so a set. A set is just collection of things, right? And we'll use this notation. We'll say that there might be an element in a set. There might be a thing that's in that set. And if there is, we call that thing perhaps omega. And we say it is in, with this funky looking E symbol, it's in a set A. So if that element is in the set, if omega is in the set A, we say, we use this notation. If we want to say that it's not in that set, then we just negate it, just like we negate an equal sign. So in this case, omega is not in the set A. We have this notion of subsets. We can compare different sets and say which sets have items in that set and which sets don't. Right? So in this case, we have A is a subset of B. That just says that every element that's in A is also in B. The equality there, or that straight horizontal line, just says they could be equal. So in fact, A and B could be exactly the same set. A more strict version of this subsetting idea is to say that A is a proper subset of B. And in this case, we just use that C symbol without the line underneath. And we say that A is a proper subset of B. And so first off, that means that every element in A is an element of B because it is a subset. But it also means that there's some element in B that is not an element in A. And that's what makes it proper. All right, so we're also going to be having this notion of a sample space. Omega oftentimes is called a universal set, but because we're going to talk very quickly in the context of experiments and what can arise out of the experiments, we're going to call this a sample space. And that is just a set of all possible events in this experiment, or said another way, all possible things that could be in any set that we're looking at. All right, so just here's some examples. If we think about having two six-sided dice, so here they are, two six-sided dice, and we're going to roll them both. So we roll them, and then we look at the upturned faces, say in this case a 1 and a 5, and we calculate their sum. The sum is 6. And if we think about all the possibilities on these 6-sided dice for their possible sums, that is going to be the sample space for this experiment, where the experiment is us rolling these dice. And the possibilities there are the integers 2 to 12. So there it is. So that's omega. That's all the possible outcomes of this experiment that there are. And now we can think about what elements are in that set and what elements are not in that set. And so, for instance, 2 is in that set. 1 is not in that set. The set 2, 3, 4 is a proper subset of the set omega, because 2, 3, and 4 are all three are in omega, and there's at least one element, say 5, that's not in omega. So it is the set 2, 3, 4 is a proper subset of omega. So that's just some examples of how we might use this notation. Okay, so now let's talk a bit about some set comparisons, some set operations, some additional terminology. So there are a number of different set operations, and I'm going to define these primarily in terms of two sets and what can be done with two sets. And so one thing that can happen is that you can take two sets and you can combine them. And when you do that, that's called the union. So the union mathematically is just every element that is in either A or in B, if we're looking at the union of A and B. Another operation is called the intersection. So the intersection operation is just if you have two sets, what elements are in both those two sets? So mathematically, the intersection between A and B is just all the elements that are in A and in B. So I often get these two confused in my mind, and so I try to remember that the union relates to or. So is it in A or B? And the intersection relates to and. Is it in A and in B? But I understand if you're confused initially. All right, so a couple other operations. We have the complement. So the complement, there's an implied universal set that we're going to be using omega for. And when you say the complement, what you really mean is that it's all the elements that are not in a set that you're taking the complement of. In the example here, we're taking the complement of A, so it's all the elements that are not in A, but that are in our universal set omega, or our sample space omega. So that's the complement. Then we have the next operation, which is the set difference. So the set difference is just, say, A minus B is all the elements in A after, and then remove all the elements that are in A, but that are also in B. Right? So if we write this out, we might say that omega, that is the elements that are in A set difference, or set minus B, is all the elements in A that are not in B. Okay, so it's often helpful to look at these set operations as Venn diagrams. I have a longer video just talking about Venn diagrams, so I'll put a link up here. But basically, Venn diagrams are a representation of these sets as geometrical objects in space, typically represented as circles. And so what you can think about is you can think about that circle, say that represents the set A, so that's the circle on the left. That circle, if you just draw the circle, then all the points inside that circle are in that set A. And then you have the set B, and all the points that are in that circle for B are the elements in that set B. And so now we can start thinking about, all right, what is the union? Well, the union is all the elements that are in A and in B, so that is now colored in this picture red. So all the elements there that are all the area is all the elements, all the area that is red is all the elements that are in A and in B, that are the union of A and B. I guess I should mention that in these Venn diagrams, there's also this universal set that is sort of everything that's outside of A and B. Well, it includes A and B as well. Okay, so then we have the intersection. So we have a set A here and a set B here, and the intersection is just the area of those where those two overlap, because that is the area or the elements that are in A and in B. The complement, so in this example we're taking A complement, so we're taking all the elements that are not in the circle for A, that are in omega, the area around A. We can also take the set difference, A minus B, so that takes all the elements in A, but subtracts off the intersection between A and B, because those are the elements that are in A and in B. And that's why we get this sort of partial moon looking red area. Okay, so it might be helpful if, as we're going forward and talking about additional operations that you can do with sets, to think about them in terms of Venn diagrams, right? Take out a piece of paper, draw some circles, and make sure that you understand what's going on. All right, so here's an example, going back to these two six-sided dice rolls and looking at their sum. So we've rolled some dice, or we're going to roll some dice, and we want to think about some of these operations in the context of rolling those dice. And so we're going to set up a couple of sets here first. So we have, again, omega is 2 through 12, the integers. And a new set that we're going to talk about is all the odd rolls. So all the odd rolls, right, are just 3, 5, 7, 9, and 11. And we're going to call that the set A. Another set that we're going to talk about is all rolls below 6. So that is B is equal to, we're going to call the set B. It's 2, 3, 4, 5. And so now we can talk about unions and intersections and complements and set differences with these two sets. And so you should maybe pause the video again right now and do all of those, and just so you can make sure that you understand. And of course, you can also change the order and say, okay, well, what's B union A? And what's B set difference A? And just verify that you understand how to take those up, how to work with those operations and these particular sets. I did a couple of them here for you. If you take A union B, again, that's all the elements in A and in B. So that is just the set 2, 3, 4, 5, 7, 9, and 11. You can take the intersection of A and B. That's just the elements that are both in A and in B. That is the elements 3 and 5. A complement, as a reminder, you're thinking about this in the context of the universal set or sample space. In this case, that is the integers 2 through 12. So A complement is just all those numbers that aren't odd. So it's all those even results. So 2, 4, 6, 8, 10, and 12. Okay, let's see. B complement, right? You can just see it's all the rolls 6 and above. So that's 6, 7, 8, 9, 10, 11, 12. We have set difference A minus B. We're just going to take all the elements in A and remove the elements that are also in B. So we have 7, 9, and 11. I think that's all the examples I have. Let's go. Oh, no, I did B set difference A as well, just to make sure you couldn't do it on your own. Or if you did do it on your own, now you can check your answer. So we have 2 and 4. All right, so that's just some examples of using those set operations. All right, so there's some additional operations terminology. The first one is going to be the empty set. So there is this notion when dealing with sets of a set that has nothing in it, and that's called the empty set. And sort of by definition, that empty set is a subset of every other set. And so therefore, this empty set is represented by sort of a circle with a slash through it. The empty set is a subset of every other set A. If A had any element in it, then it would be a proper subset. We can also have a property of two sets called being disjoint. That just means that those two sets have no elements in common, and therefore their intersection is the empty set. If you have a whole collection of sets, or a set of sets, if you will, that collection can be pairwise disjoint, and that just means that every pair of sets has no elements in common, or every pair of sets is disjoint. All right, the last on this slide is De Morgan's laws. So De Morgan's laws just basically allow you to convert back and forth between unions and intersections. So if we have A union B, then complement, that's the equivalent to A complement intersection B complement. If we have A intersection B complement, then we can do A complement union B complement. And this is one of those circumstances where it might be helpful to take out the Venn diagrams and work your way through. Figure out what the union of A and B is, then figure out what the complement of that is. And then verify that if you do the right-hand side of the equation, that is, you take A complement, then and B complement, and you take their intersection, then you get exactly the same set. All right, so here's some examples working back with those these dice that we've got here. We now have 4 different sets. We have the set 2, 3, 4, then the set 5, 6, 7, then the set 8, 9, 10, and then the set 11, 12. And we've called them A, B, C, and D, respectively. And so now you can say A and B right, their intersection, they have no elements in common, so they are, right, that's the empty set, and they are therefore disjoint. If you look at A, B, C, and D, and you try to take any pair and take their intersection, you'll find that that intersection is always the empty set, and therefore they are pairwise disjoint. Here you could use due to Morgan's laws. Here we have A union B, so that's just the integers 2, 3, 4, 5, 6, 7. If we take their complement, right, we're thinking about this in this sample space 2 to 12. So the complement then is going to be 8, 9, 10, 11, 12. So that was the left-hand side of De Morgan's law from the previous slide. Now we're going to do right-hand side. So the right-hand side says, okay, let's take A complement. Well, the complement of 2, 3, 4 within this sample space 2 through 12 is just 5 through 12. There's the complement. Now we do B complement. So B is 5, 6, 7. The complement there is going to be 2, 3, 4, then 8, 9, 10, 11, 12. Now the last step of De Morgan's laws, because we are using union on the top part here, we're going to use intersection on the bottom. So we're going to take A complement, B complement, and take their intersection. Well, their intersection is just the elements that are in both, and that turns out to be 8, 9, 10, 11, 12. And therefore, at least by an example, we've seen that De Morgan's law holds. Okay, so we are now all set up to define probability, right? So that was the breakfast, the healthy breakfast that we had to eat in order to get to talking about probability. So probability is just a set of rules, and this set of rules basically says if you want to take a function P, that is the probability, of a set or an event A, where A exists in some sample space omega, so A is some subset of omega, then here are the rules or axioms that that probability has to abide by. So the first thing is that it has to be a number between 0 and 1 for every possible subset of that sample space. So this hopefully makes sense based on your history or your knowledge of probability. Right? When people talk about probabilities, it's a number between 0 and 1. Oftentimes it's portrayed as a percentage, right? Which is then a number between 0 and 100%, right? Which is really just a number between 0 and 1. Right, so that's the first rule. The second rule here is that the probability of the entire sample space is 1. So that's the probability that one of these events has to occur, right? So if we're talking about rolling our 2 6-sided dice and adding up their total, right, then it's got to be a number integer between 2 and 12. All right, so that seems reasonable. Now the last one is a little bit trickier. And the last one says, let's suppose that you have a whole collection of pairwise disjoint sets. And we're going to call that A1, A2, and so forth. And there's possibly a countably infinite number of them. Right? So there's an infinite number of them, so you can just keep going A1, A2, A3, A4, A5, A6, on up and never stop. So that's possibility. But the key here is that that collection is pairwise disjoint, which means that for any pair, they are disjoint, that is, their intersection is the empty set. And that's key because now no two sets have any elements in common. So when an event occurs, it can only be one of those particular events that occurs. Okay, so now if we want to calculate the probability of the union of any number of those sets. So here I've represented it as A1, A2, A3, but that numbering was really arbitrary. And so you have the union of any collection of those sets. It could possibly be the infinite union, but doesn't have to be. Then the way that you calculate the probabilities is just to sum up the probabilities for the individual sets. Okay? And so that is our third axiom in these Kolmogorov axioms. And maybe I should have mentioned at the top, an axiom is just a set of mathematical rules that we decide we're all okay with. Okay? So you should stop right now. Again, perhaps stop the video and say, am I okay with these axioms? Is there anything I don't like about these axioms that I want to complain about now before we go forward and we use them? But generally, people seem to agree that these seem like a reasonable set of criteria for calculating a probability. Okay, so those are Kolmogorov's axioms that and a couple of new definitions that we'll get to basically provide the foundation for probability. Okay, so I want to make a comment about these axioms and whether or not they lead to helpful probability models. Okay, so the key thing here is that in order for something to be a probability model, it has to obey those axioms. But any system that obeys those axioms is a probability model. So there's then a question about whether that probability model is at all useful. And so here's my, really cheesy, dumb example. Suppose that we're going to draw a single card out of this well-shuffled deck of cards. Right? So we've got this well-shuffled deck of cards. Probably got jokers and all kinds of things in here. Well, maybe not. Right? So that was I did it off camera, but it was really well shuffled. All right, so we've got this well-shuffled deck of cards, and we're going to draw the top card off. Right? This time it happens to be red. And that's all we care about. Is it red? Is it black? Okay. So, there's a variety of probability models we could actually propose here. So model 1 in this example says, okay, we're going to define that you have to get either red or black. So when you draw a card, right, let's draw the next card. When you draw the next card, right, it has to be red or black, which is fine because I haven't gotten any kind of funky deck here. It's just a normal deck of cards, so all the cards are red or black. And then you say, all right, I'm going to say that the probability of red is 0.5 and the probability of black is 0.5. But perhaps somebody else, or perhaps me on an off day, says, I've got a different model. Again, you have to draw either red or black cards, so that stayed the same. But I'm going to say that the probability of red card is 0.3, and the probability of... There's the red card. Probably red card is 0.3, the probability of the black card is 0.7. And now, if you are using a normal deck of cards, it seems very clear that one of these two models is the more realistic model. Right, that is, half the cards are black and half the cards are red, so model 1 makes a little more sense from a realistic standpoint. But I want to comment now that both of these models, I think I make it here, are equally valid probability models under Kolmogorov's axioms. Right? So the axioms say nothing about whether that a model is realistic for the real world. Okay. But again, for this example, I think that we would all say that model 1 is more realistic for a normal deck of cards. Okay, all right. So there are some, it turns out, that you might have wanted to add a lot more rules to probability. There might be things that you actually understand about probabilities that you might have wanted to add to those axioms, but it turns out that this small set of axioms actually provides us a lot that we can derive from it. And so that's what this page is about. Here we have useful consequences of Kolmogorov's axioms. That is, things you can prove based on the axioms. So if you have two sets A and B that are in the sample space omega, it turns out that the probability of the complement of A is just 1 minus the probability of A. Right? So if I wanted to say, what's the probability of getting a red card, and I already knew what the probability of getting a black card was, I could just take 1 minus that and I would find out the probability of getting a red card. Right? That's extremely useful, and it turns out you can derive that from Kolmogorov's axioms. From that, you can determine that the probability of the empty set is 0. Right? Again, the empty set is the event that nothing happens, right? And the probability of that is 0, which makes sense because we already talked about, well, something always has to happen. All right. There's an additional rule here that you can derive, and that is, what if you have two sets or events, A and B, that are not disjoint? That is, that they have some elements in common. But now you want to calculate the probability of that union of those two events. Well, it turns out what you can basically do is you can say, all right, I'm going to take the probability of A and add to it the probability of B. But now I know that there are some elements or outcomes that are in common between these two that I've double counted. And so I'm going to subtract them off. And those that I've double counted are the intersection between A and B. And then finally, I guess I missed a pause there. Finally, if A is a subset of B, then the probability of A is less than or equal to the probability of B. I should maybe stop at this point and say that if you want to try to visualize probability, it's a good idea to go use Venn diagrams, and maybe go back to that video that I have on Venn diagrams. when you think about probability in the context of Venn diagrams, what you should think about is that the area of those geometrical shapes, say circles, that area is the probability. And so if you do that visualization, you can, this second bullet point, this addition rule, you can say, all right, if I'm calculating the probability of A, that's the area related to circle A. And if I'm doing the probability of B, that's the area of circle B. If I add those two together, then I've double counted this sort of oval football looking shape, right, in the middle. American football, that is, right? That shape in the middle I've double counted, and so I need to subtract it off. And that's exactly what's happening in that addition rule of probability. Okay, so all right, now let's talk about a couple of uses of Kolmogorov's axioms through an example. So let's go back to that example of having you're trying to connect to the internet, right? You have a Wi-Fi system at home, and then there's the ISP that you have to go through to get there, and of course there's much more going on beyond that. And let's suppose that based on prior experience, you have some information about the relevant probabilities of different components being up. So in particular, let's suppose that you know that your Wi-Fi is okay, it's up 90% of the time. The ISP is horrendous, their advertised rate is only 60% uptime. And you know based on prior experience that your ability to connect to the internet is that you can do it about 55% of the time between the Wi-Fi and ISP. So using this information and Kolmogorov's axioms and the consequences thereof, you can actually calculate many more probabilities. So for example, there might be, what's the probability of the Wi-Fi is up or the ISP is up? What about the probability that both the Wi-Fi and the ISP are down? And perhaps more importantly, what's the probability that you fail to connect, that you cannot connect? Now using the axioms and consequences and these three probabilities, we can answer those questions. You might want to pause right here and try to do it for yourself right now. Alright, so here's the solution, or one way to solve the problem. There are of course many different ways to solve the problem. We're going to let A be the event that the Wi-Fi is up, and B be the event that the ISP is up. The first question says, what's the probability that Wi-Fi is up or that the ISP is up? And so if we're going to write this in our set notation, that is A union B, because there can be either of those two occurring. And then if we use the consequence that we calculated before about the additive rule, the probability of A or B is just the probability of A plus the probability of B minus the intersection of A and B, which is that they are both up. So we have this 0.6 plus 0.9 minus the intersection, which is 0.55, and we find that one or the other of them is up 95% of the time. All right, what is the probability that both the Wi-Fi and the ISP are down? So one way to solve this is say, okay, well we have these events or sets that are that both of them are up, and we can take their complement. That's the event that they're down. So we have A complement and B complement, and now we're combining them using the word and. So we need the intersection. So we have A complement intersection B complement. By De Morgan's law, that inside the parentheses for the probability, that is just A union B complement. And so we calculate that in step 1. So here we can take 1 minus 0.95 and find out that 5% of the time they are both down. The third question is, what's the probability that we fail connect? Now there's actually a very quick way, because you know how often you do connect, but there are multiple ways to solve problems. So here's the more laborious way to do it. What's the probability you fail connect? Well, you fail to connect when either the Wi-Fi is down or the ISP is down. So now we have the union of A complement and B complement. We can use the additive rule of probability here, and we say, well, that's the probability of A complement plus the probability of B complement minus the probability of A complement intersection B complement. And we can then plug in the numbers, and if we do the calculations, we find that the probability is 0.45, which again, we could have gotten much quicker because we already knew the probability that they were both up. Excuse me. We already knew the probability that they were both up, and so 1 minus that is going to be the probability that at least one of them is down, and therefore we will fail to connect. Alright, so that's an example of using these Kolmogorov's axioms and their consequences and rules from set theory, De Morgan's laws, and so forth to calculate relevant probabilities. All right, so the next step is to say, all right, so we have probability, we have the definition of probability through the axioms. Sometimes we want to say, well, what's the probability of something occurring if we know something else occurred? And we get into conditional probability in order to make those kind of statements. So here's new notation. We have probability of A, this vertical bar or pipe, B. And the way that we read that is the probability of A given B. And the idea there is that we know B occurred, so then what is the probability of A if we know that B occurred? And so if you want to think back to our example of throwing some dice here, right, you might say, what if we knew the result was odd? Well, then what's the probability of 1? Something like that. Okay. All right. So the definition for this conditional probability, that is the probability of A conditional on B occurring, is just the probability of A and B, so the intersection between A and B, divided by the probability of B. And we know we can't divide by 0, and therefore the probability of B must be non-zero, and since probabilities are always positive, it must be greater than 0. All right, so that's the definition for conditional probability. As an intuition here, the way that I think about this is that you have the fractions of outcomes in B that are also in A. And so if you think about your Venn diagram, right, and the probability is the area of those geometrical shapes, say circle in the Venn diagram. And what you're doing here is you're saying, all right, let's narrow the scope of the entire problem from the whole sample space omega just down to B. So here's the circle for B, and now what portion of that area includes A? That portion is the numerator, the denominator is that whole area for B. All right, there's a corollary here. You can you can rearrange things and write the intersection, the probability of the intersection of A and B. Well, that's just the probability of A given B times the probability of B. But of course, we could have reversed A and B, so that's also equal to the probability of B given A times the probability of A. Because these sets A and B are just arbitrarily decided, and so we could have them in either order. All right. As an illustration of conditional probability, I will use an example of an imagined bucket full of central processing units, or CPUs. This table has an indication of how many CPUs of 2 different speeds and whether those individual CPUs are defective or are good. And so you can see, for instance, there are 490 of the 1,000 CPUs in this bucket that are 2.0 gigahertz and that are good. And so if we think about identifying G with good and D with defective, and we might be trying to ask ourselves this question. If we selected a CPU at random and we observe its speed, then what is the probability that the CPU is defective given that we saw that its speed was 1.8 gigahertz? And so we could do this directly from the table, and we'll use that in a second to verify our answer. But first, let's use that definition of conditional probability. So the definition of conditional probability said that if we need defective given the speed, then what we're going to do is we're going to say what is speed and defective, the intersection of those two events, what's that probability, and then divide by the probability of that particular speed. And so there are a couple of quantities we need. The first is that we need to know what the probability of getting that speed is. So that's probability of speed. There's 500 out of the 1,000 CPUs, and so therefore the probability of getting at random a CPU with a speed of 1.8 is 0.5. Now we have the probability of the intersection of the two events of the speed being 1.8 and the device being defective. Well, we can see from the table that there are 20 out of the 1,000 CPUs that have both that speed and that are defective. And so we have a probability of 0.02. Now the definition of conditional probability said to find the probability of being defective given the speed is 1.8. We take the probability of the intersection between those two events, which was 0.02, and we divide by the probability of the quantity or the event on the right-hand side of the conditioning bar, in this case the probability of the speed being 1.8. That probability was 0.5. We take that ratio, 0.02 divided by 0.5, we get a probability of 0.04. Now again, we could have gotten this directly from the table. We can just look at the table and say, here's the column that has a speed of 1.8. In that column, we have 20 defectives out of a total of 500. If we take that ratio, then we get exactly the 0.04. And so for this particular illustration, it's good because we can check our answer, but we could have gotten the answer directly. All right. So the next topic here is a topic of statistical independence. And out of the whole slide set, this might be the most important concept. So hopefully you're really paying attention right now. Right now we're talking about independence between two events. In future videos, we'll be talking about independence of random variables. It's very much a related concept. And so once you get this concept, hopefully you can transfer it to the discussion of random variables. So if we take two events, A and B, they are defined to be statistically independent if the probability of their intersection is equal to the product of their individual or marginal probabilities. Said mathematically, we have the probability of A intersection B, and that's equal to the probability of A times the probability of B. That's the definition of being independent. Now, sometimes we can think about situations where we are reasonably certain that things are independent. Other times, and it's an assumption we have to make, we might be able to test whether or not that assumption is reasonable. Another way to think about this is that, and we can use the definition of conditional probability to get to this answer, we can think about finding the conditional probability of one event given another. In this case, the probability of an event A given an event B. And it turns out that if the two are independent, then this is just the probability of A. And so intuitively, the occurrence of one event doesn't change the probability of the other event, right? And it's also true that the non-occurrence of one event doesn't affect the probability of the other if those two events are independent. As a more realistic example, if we have a coin here that we're flipping and say we do the first flip and we get a, what is this? That was a tails, right? Then that doesn't affect the probability of flipping a heads on the next flip or a tails on the next flip. Right, that first flip is entirely independent of that second flip. Okay, so here's going back to our simplistic trying to connect to the internet example. We have our Wi-Fi being up or not and our ISP being up or not. If we assume that those two are independent, which for the most part it seems pretty reasonable, then we can just calculate the probability that I can connect to the internet, which is the intersection of those two events, by assuming that they're independent. It's just the product of their marginal probabilities. So as a reminder, we had I swapped these. It used to be the ISP that was terrible, and now it's my Wi-Fi network that's terrible. But let's say that my Wi-Fi network is terrible, and it only has a 60% chance of being up, but the ISP rather, is up 90% of the time. Then in order to find the intersection, that is the ability to connect to the internet because both of those events are true, we just take the product of those two right here. So the probability of their intersection, if we assume independence, is equal to the product of their marginal probabilities. In this case, the product is 0.54 or 54%. Okay. I want to make a statement now that there are two related concepts, and if this is the first time you're seeing it, you might get confused between the two, and so I just want to try to stave off any confusion before we get too far. So that is this relationship between independence and disjoint events. So events can be independent and they can be disjoint, but these are two very different concepts. So in particular, disjoint means that those two events cannot both happen. And it turns out that their intersection, therefore, is empty, right? So if you again are thinking about a Venn diagram and thinking about the areas as being the probability of the intersection, because there's no area of those two circles that overlap, the probability is 0. Okay. In contrast, if two events are independent, right, then they are going to have some overlap, and the probability then of their intersection is just the product of their marginal probabilities. And the key here is that if two events are disjoint, then they are distinctly not independent, because you know if one of the event occurs, then the other event cannot occur. Okay, and so knowing the status of one of the events tells you precisely the status of the other event. So just keep that in mind. Independence, disjointedness, two completely different concepts. All right. So now we're going to move forward and we're going to talk about an application of probability and the definitions that we had so far to network systems of some sort. So in your mind, you can be thinking about a wide variety of network systems. So you can think about, as I've been talking about, the network to get to the internet. Or you can think about a particular ISP and having a set of routers. Or you can think about a social network, where it might be a network of friends where you're trying to get a message to a friend or maybe a distant relative, and so you go through your parents, and then they go through their connections, and eventually the message tries to get to the intended recipient. And so there are a number of different systems like this that we can talk about, but the systems have two distinct aspects of their structure. One is that components in the system can be put in the system in parallel, or it can be put in the system in a serial fashion. And so I'm just going to define that briefly for you here. So a parallel system, I have no breaks there, a parallel system of k components, an only parallel system, is set up such that if you're trying to go from one point to another point in this diagram, from point 1 to point 2, then you can go through any one of those capital K components. So you can go through component 1 or component 2, all the way up through component capital K. Right? And so this is a very robust system because there are many paths for you to get from point 1 to point 2. In contrast, a purely parallel system has a set of K components that are set up such that you must go through every component in order for the system to operate properly. So if you're going in this diagram from node 1 to node 2, you have to go through component 1, then through component 2, then through component all the way through to component capital K. And so this is a not very robust system because you have to hit every single one of those components has to be operating for the system overall to operate. All right, the reliability of a system is just the probability that the system is working. All right, so we had that example of the ISP Wi-Fi, right? If we assume independence, then its reliability is 0.54, or not that good at all. Now we're going to go through and we're going to talk about, in these two distinct types of systems, parallel systems and serial systems, how we can quickly calculate these probabilities. So in particular, if we have a parallel system that has capital K components, and each individual component has a probability P sub K of working. That is, component 1 has a probability of P1 of working, component 2 has a probability P sub 2 of working, and so forth. Then if we want to calculate the reliability of the system, or the probability that the entire system works, remember now, the key is that any component could work, and the system is going to work. And so what we have to have for the system to not work is all of the components to be down. All right, so the way that we're going to calculate this, the reliability of the system is the probability that the entire system works, and that's the probability that at least one of the components in the system works. The easier way to calculate this, whenever you see at least one, the easier way is to say, well, this is 1 minus the probability that none of the component of the system work, right? Or that is that all components fail. All right, so now what is the probability that a particular component fails? Well, it's 1 minus pk for the kth component. If we then assume independence, which we stated up above, if we assume independence, we can now calculate this probability that all components fail by just multiplying by the product of their individual failure probabilities. Okay, so here we go. There's the 1 minus the product of their individual failure probabilities. We define that to be P sub k. So there's the 1 minus P sub k. Sorry, I should have said that P sub k is the success, so 1 minus P sub k is the failure. All right, so anytime we have a parallel system, we can quickly calculate the reliability by just using this formula, 1 minus the product of 1 minus their individual probabilities of succeeding, or individual component reliabilities. All right, now we move over to serial systems. So in a serial system, as a reminder, every component has to work in order for the system to work. And so if we want to calculate the reliability of this system, then we just say, all right, the probability that the system works is the probability that all components work. This is just the product that each of the individual components work because we've assumed they're independent. And we've defined that probability to be P sub k. So the probability that the system works is just the product of the individual component probabilities P sub k. Okay, so great. So let's get to a more realistic example of a system that combines both serial and parallel components. So here's a system. It's set up with 5 components, A, B, C, D, and E. And there are essentially 3 paths that go from the left-hand side to the right-hand side. You can go the upper path, which goes through A, B. You can go through the middle path, which goes C, D. You can go through the bottom path, which goes C and E. And the way that we're going to tackle this in terms of calculating reliabilities is we're going to think about subsystems that are entirely parallel or entirely serial, and then calculate that subsystem reliability, and then sort of, in our minds, create a new component that is that subsystem. Okay. All right. So let's suppose that in this system, each of the individual components has an individual probability of operating correctly of 0.92. Okay, so that is A and B and C, D, and E all have a probability of 0.92 of working correctly. Now we can see that that path on the top, AB, that is a serial system, right? If you're going to go on that top path, you have to go through both A and through B. So we're going to replace that top component with a new sort of pseudo component that has the reliability of A and B together. Now, in order for a serial system to work, we have to multiply their individual probabilities. And so for that first component to work, we do 0.92 times 0.92 or 0.8464 probability of that AB component working. Now we have another component in this diagram. We have the DE component. The DE component, just that subcomponent, or that subcomponent, is a parallel system. So in that parallel system, we can replace that DE by calculating the probability of that subsystem working. And if you remember, the probability of a parallel system working is 1 minus the product of 1 minus their individual probabilities. And so we can calculate that, in this case, 1 minus the quantity, 1 minus 0.92 squared. And we find that the reliability of that DE component is 0.9936. All right, so now we're going to replace AB with a new component, and we're going to replace DE with a new component. So here's what the new diagram looks like. So AB is replaced with F, and DE has been replaced with G. And now we have to remember, or look back at the previous slide to remember what their individual component probabilities are. If you look at the bottom now, this CG component is a serial system. That serial system has an overall reliability that's equal to the product of their individual reliabilities. And so we have the reliability of C, which was 0.92, and the reliability of this pseudo component G, which was 0.9936. We multiply those two, we get 0.9141. And now we're going to replace that bottom line with a new pseudo component called H. And now we have 2 components, F and H, and they're now in a parallel configuration. So we use the parallel formula, which is 1 minus the product of 1 minus their individual component reliabilities. And so we have the formula there, and it turns out that overall the reliability of the entire system is around 0.99. One thing I want to comment on is that as you're doing these calculations, you should keep all the significant digits while you're doing the calculations, but then at the very end, round to something reasonable. In this case, 2 digits seemed pretty reasonable. All right, so here reliability, we've gotten a practical application of the rules of probability. Now we got to go back to set theory and talk about a property that a collection of sets can have called a partition or a cover. And it's a partition of some bigger set. In this case, we're going to talk about omega as being the universal set. And the 2 key properties that a partition have is that they're pairwise disjoint, which means that the intersection of any 2 of them are empty. And secondly, that if you take the union of all of these sets, you get back the set that you were originally interested, omega. Okay, so here's a picture of what's going on. The picture shows no overlap between any of the sets B1 up through B capital K, and it shows that this collection of sets covers the entire space that we're interested in, omega. Okay, so pairwise disjoint, and their union covers the entire set. All right, we're going to use this. We're going to give an example first. Here we're going back to our rolling dice example. Going back to our rolling dice example and looking at the sum of 2 rolled 6-sided dice, and we have the overall collection of sets. Collection of outcomes is the integers 2 through 12. There are many different ways to construct a partition of this particular set. Here are some partitions. We have 2 sets, 2, 3, 4, and 5 through 12. We have another 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, which we saw earlier. we have a collection of sort of these singleton events, right? So each individual event is just the individual outcome. So 2, that's an event, or 3, that's an event, 4, so forth, up through 12. We could think about any set that we want to think about and its complement. Those two always form a partition, and sometimes that's the most convenient partition that we can have. And one of these could even be the empty set, and that's still okay. It might not be useful if we're doing any calculations, but it's okay. Okay, we're going to apply this idea of a partition to calculate something called the total law of probability. So imagine that what you're trying to do is calculate the probability of an event A, but for some reason it's difficult to calculate that probability. And so what you're going to do is you're going to break that probability up into a set of a bunch of smaller probabilities. And you're going to do it through a partition B1 up through BK. And then what you're going to do is you're going to calculate the probability of A given that partition BK and multiply it by the probability of the partition element BK. And then you're going to add all of those up. And if you look at the product after the sum there, the conditional probability of A given BK times the probability of BK, and you go back to the definition of conditional probability, it turns out that that's just the probability of the intersection of A and BK. And that, in a second, when I show a diagram, might provide some intuition in terms of why this is true. Here's the proof. You can go ahead and pause the video right here and take a look at the proof, but it's pretty quick. All right, so graphically, here's what's going on. So we have some space omega, and all these sets would live within that space. We have some event A that we're trying to calculate the probability of, and say that it's hard to calculate, in this case, in this Venn diagram, to calculate that area. And so what we're going to do is we're going to take a partition. In this case, the partition I've constructed are just these vertical rectangles. And we're going to calculate the areas of A that intersect with those individual partition elements. So for instance, B1 has no overlap with A, so that intersection is just 0, or the probability of that intersection is just 0. But if you go to B2, now we have the intersection between A and B2, and that's just some area there that we have to calculate. And we do that for each of the individual partition elements, and then if we add all of those individual elements up, what we will get is that area of A. And hopefully, graphically, this depiction convinces you that that would be true. And now, one way to calculate that intersection probability is through a rearrangement of the conditional probability definition. And so we could calculate the probability of B2, for instance, in omega. And then we can calculate the probability of the area in A that's also in B2, right, as a ratio between that and the area in B2. And between those two, we can do the product, and that gives us the total law of probability. All right. Here's an example. I don't know if I mentioned craps, the rules yet. There's a craps of the game played with 2 dice, 2 6-sided dice. These 2 6-sided dice are rolled in what's called the come-out roll. The come-out roll, you automatically win the game if you roll a 7 or an 11. And so right here, we're going to use that to calculate some probabilities here. So the probability that you win, right, can be written using the law of total probability. That law of total probability says what we have to do is we have to have a partition. So the partition that we're going to use is just all the possible rolls that we could have. So one event is 2, another event is 3, another event is 4, and so forth. And now we're going to calculate the probability of winning given that roll times the probability of that roll. And now it turns out that this one is pretty simple because if you rolled a 7 or an 11, you automatically win, so those probabilities are 1. If you rolled anything else, those probabilities of winning given that roll are 0. And so all we end up having is to add the probability of rolling a 7 and the probability of rolling an 11. It turns out the probability of 7 is 2/9, probability of 11 is 1/9. You can add those up, and you get 3/9 or 1/3. Okay, so Bayes' rule. So that's an example using the total law of probability, a pretty simplistic example. We're going to use the total law of probability more often when we're trying to calculate something called Bayes' rule. So again, we need this partition, call it B1 up to BK, and we need an event A. And now what we're going to try to do is we're going to try to calculate the probability of one of those elements in the partition given that A occurred. And really all we have here is a double application of the definition of conditional probability. And that double application basically says we can calculate the probability of bk given A occurred. That's equal to the probability of A given bk times the probability of bk divided by the probability of A. But then what we're going to do is we're going to expand out that probability of A and using the law of total probability. And that tells us that we can write this out as the sum of the probability of A given bk times the probability of bk, and do that for k from 1 up to capital K. So this is something called Bayes' rule, and the very convenient aspect of Bayes' rule is the fact that you can switch the conditioning. That's the way you should be thinking about it, right? So notice on the left-hand side we have bk given A, but then on the right-hand side we have A given the bk's. Okay, so that's the key intuition here with Bayes' rule, is being able to flip that conditioning. Here's a quick proof. Again, if you want to look at it, it's just what I walked through, but you can pause the video and take a look at it. All right, so if we go back to that simplistic example of the come out, roll, and craps, suppose we reverse the idea. Suppose somebody said, hey, you won, but you didn't actually see what you rolled. You can calculate, well, what's the probability that you rolled a 7, given that you know that you won? And so we can calculate the probability of rolling a 7, given that you won. This is just now if we want to flip that conditioning, the probability of winning given 7 times the probability of 7 divided by the probability of winning, right? Which by the law of total probability, we calculated before. The end result is that you have the probability of 7 divided by the probability of 7 plus the probability of 11. It turns out, right, via the calculation I did before, we had 2 9ths and 1 9th. So this is 2 9ths divided by 3 9ths, which is 2/3. So that's the probability that you rolled a 7 if somebody told you that you won. Okay, now a more interesting example perhaps. Go back to some of our CPU ideas, but now imagine that you're a manufacturing facility and you know that your line produces on average 2% defective CPU chips, right? And so because you manufacture some defective chips, you're going to get each of the chips tested. As they come off the line, they get put on a device and they get tested. All right. And then the tester itself, though, isn't 100% accurate, just like any other test out there. But it's pretty good. Let's suppose that if the CPU is good, it tells you the CPU is good with a probability of 0.95. And if the CPU is bad, it tells you it's bad at a probability of 0.94. All right, so now the question is, you've got a particular CPU, it's gone through the line, it's been tested, and the tester said that that CPU is defective. Now the question is, what's the probability that it's actually defective? All right, so you'll notice here, if we want the probability that it's defective, given that it tested that it's defective, that's the opposite of the conditioning that we have above here, right? So the probabilities that we have is the tester saying that it's defective given that it was actually defective, right? But we want to flip that conditioning. We want what's the probability that it is defective given that the tester said it's defective. Okay, so we're going to introduce some notation here to work our way through the problem. CG is the event that the CPU is good, and CD is that it's defective. TG is that the tester said it's good, and TD is the tester said it's defective. And now from the problem description, we know a number of probabilities here. So we know that what's the probability that the chip is defective overall before we got it tested? Well, we know because the production facility produces 2% bad chips at 0.02, that's the probability of the chip being defective, which is also 1 minus the chip being good because those two form a partition. Now the 0.95, that's the probability the tester said is good given that the chip is good. And then we have the 0.94, that's the probability that the tester said it's defective given that the chip is actually defective. And both of these, because we have the tester being good or saying good or bad, we have a partition there, so we can calculate these other probabilities like 1 minus the probability the tester said it's defective given that the chip is good, or 1 minus the probability that the tester said it's good given that the chip is bad. And those will come into play in a moment here. All right, so now what are we trying to do? We're trying to calculate the probability that the chip is defective given that the tester said it's defective, right? So chip is defective given that the tester is defective. If we just plug in Bayes' rule, here's what we have. The partition we're using here is that the chip is either good or the chip is defective. And so then we just work through the math and we figure out some of these places where we need the opposite piece of the partition, so we can change the second some piece in the denominator. Now we can just plug in some numbers. If we plug in some numbers, we find that the probability that the chip is defective, given that the tester said it's defective, is only 0.28. So the chip very well might still be good, and what we probably want to do is go send it on to a better tester, right? This might have been a screening test or sort of a quick and dirty test, but the next tester might be much better, but it also might be much more expensive to run. All right, but the good side is we haven't immediately lost a chip out of our production line. Okay. All right, so that was a lot. Right, there's a lot there. We went through probability. We started with interpretation. I hope everybody was keeping in mind that interpretation, the frequentist idea and the personal belief idea. We went through some set theory, including things like partitions. We talked about Kolmogorov's axioms of probability that lays out the mathematical foundation for probability. We talked about a definition for conditional probability. We talked about events being statistically independent. We applied those ideas to reliability in systems. We introduced this total law of probability primarily for using within Bayes' rule, and then this chip testing example in Bayes' rule. In our next video, we're going to start talking about random variables, and in particular, discrete random variables. Until then, I hope you have a great one.